All right, let's see. So we want to discuss the RAOs today, right? Let's take a look. All right, let's get started.
Hello everyone. Today we are going to present a seminar based on determining response amplitude operator for pitch and heave motions of crystal container ship. And people working on the study are Manoranjan, Vallabh, Aditya, myself Saket, and Krishnavelu. And so today's presentation will proceed first by stating the objective of the study and abstract. And then the audience are introduced to the concept of response amplitude operator and its importance in hydrodynamic applications. Then the experimental model setup used for data collection, which includes the mooring spring system, is also explained. And to get the wave parameters, we generate a test matrix of time period and wave height in the wave basin. Uh, and the data collection and various sources involved, like Hydra and so on, are also discussed, along with the data analysis, which is done by using MATLAB. And we also present the results obtained until now and the work completed. And at the last, we discuss the further steps to be taken and expectations to be discussed. And now, next slide. So in our abstract, now our study is mainly focused on determining RAO for pitch and heave. And in our study, we have considered the head C condition. The experimental data is compared with the results obtained from hydrodynamic response analysis simulation, which is also called Hydra. And the comparison is essential for the validation of Hydra simulation. So then this study is also conducted on a full scale ship using Hydra simulation. Next. So the RAO is the response ratio of amplitude of motion to the amplitude of wave, and it describes the responsiveness of the ship to the external effect of the waves in a particular motion. The vessel is subjected to different orientations of the wave, along with the range of frequencies, as the sea condition and frequency are also affect the wave forces, which then in turn affect the RAO. So it depends on the RAO also depends on the hull form of the vessel, as different hull forms respond differently to the wave excitation forces. So RAO are also calculated for all 6 degrees of motion. But we discuss in our presentation, we only discuss pitch and heave RAO. And RAO, at last, RAO is dimensionless because it's the ratio of amplitudes. There are many purposes of RAO in designing of floating structures and ships, where the hull form is subjected to a wide range of conditions in open seas. RAO provides insight about its responsiveness and efficiency, and it also gives us an intuition about the behavior of the ship when we are operating at the sea. Now I'll hand over the presentation to Manoran.
So now, whenever we are going to conduct the sea keeping test, at that time we need to hold the model at particular place. That time only we are going to get the response from the vertical plane motions. So how can we achieve that by using the mooring line that is in the spring means? So we need to choose the suitable material of the spring as well as the spring constant. So that time only we are going to hold the model at particular location, does not drift away from that particular that location. So here we are choosing the spring. Spring constant is the K is equal to 6 Newton per meter. So before the test, we are already made for the three set of the springs. Like one is the 3 Newton per meter, another one is the 6 Newton per meter, and the last one is the 9 Newton per meter. We will conduct the roll TK test. So that time, so with spring and without spring, natural frequency of the model with spring and without spring should be same. So that which spring is going to perform, which spring is does not affect the natural frequency of the ship. So from the test we are identified this particular spring 6 Newton per meter only does not affect the natural frequency of the model for the all the responses. So that's only we are choosing this spring constant. So here, this second picture, the right side picture shows the how we are hold the model at the center of the wave basin. So then only we are going to generate the wave. That time only we are going to obtain the response of the ship. Next slide. So whenever we are going to generate the waves in the wave basin, we need to develop the test matrix. It's very important for one, which means we know the full scale of the ship. Now we are fruit number used to make the model scale. The similar way we are going to we need to develop the test matrix for the what kind of the waves. It means which means in particular time period or particular wave height we are going to generate in the wave basin for the each and every test. So generally we know that our gravity wave have the time period of and the varying time period of 2 to 20 seconds. But we are just interested to focus on the 10 to 20 seconds. At that time, so 10 to 20 seconds. So then only we are going to generate the wave exactly what happened in the open sea condition. That is also we are represent in the model scale in our wave basin. So then we know that we don't know what's the wavelength in the open sea. So but we know our length of the ship in the full scale. So now we are using the ratio between the wavelength to the ship length is equal to 1. So these things are used to get our the time period. So here we are using the dispersion relationship. We know that. So here the dispersion relationship used to get the time period in the open sea in the real sea condition. So that time period is the 12.142. So from the time period to we can able to get the time period in the what way we are going to generate in the wave basin. So which means we know that the root number formula. So Tm is equal to Tp divided by square root of the square root of scale ratio. This way to we are getting the 1.40 seconds. So now we are find out that 1.40 seconds. From that we are going to get some ranges from the. So now we are considering 1.40 is the center portion. We are considering ranges from the 0.9 to 2. So this is our test matrix. Here in the 11th case number it shows the 1.40, which means we are already know about our length of the ship as well as the length of the wave should be is equal to 1. That's also showing in the column 4. So the same way we are going to catch up the wavelength from 0.5 to 2. So here now we are considering the time we are considering that take the time period range it becomes from the 0.9 to 2. The same way we are going to using the dispersion relationship going to get the determine the wavelength. In similar way we are going to determine the wave height. It depends upon the different wave steepness. We know that the different wave steepness or wave slope formula H by lambda is equal to some value. So that way we are going to find out the wave height for the different wave period. So each and every wave period we have the wave height. The wave height it will be varying for the different wave steepness. Next, I hand over to the developer. Yeah. No. So now we are conduct a test in our wave basin. So can you play the video? Yeah. So now we are going to generate the. Now we are giving the input to the system. The system will give the comments to the wave maker. Then the waves are generated in the wave basin. So from that particular wave data we can able to collect from by using the wave probe. So the wave probe data we can able to collect the wave profile. So then we are going to collect the IMU and GPS data. So we can able to do that in the two way. One is the wave our extents on the phone. These two things are already inside the model. So the two things are helpful to collect the data. It depends upon the response of the system. So then these data we are used to proceed for further calculation process. Slide, hello.
I have a doubt.
Yeah.
So why do we use the GPS data from the phone?
No, we are going to collect the data from the mobile. We are going to collect the IMU plus GPS data from the mobile. But we don't know it does not working. We don't have the good data. It may be some error is there in the GPS data.
No, it's not moving, right? It is attached to cables.
For analyzing this whole thing, for calculating the RAO, the GPS data is not used. Only the IMU data is used.
So it's not useful, GPS data.
For calculating this RAO.
Calculating the
Yeah.
we are not using the GPS.
Excuse me. I'm not able to hear you.
No, what they're saying is they're not using the GPS data to compute the RAO, only the IMU data is used for the RAO.
Okay, sir.
The GPS is also collected just to verify how good of a lock on GPS we get inside the wave basin, especially near a ferromagnetic bridge. But
So
that
it
has
is for,
nothing to do with RAO.
so it's basically a test for the GPS.
Sorry?
It's basically a test for GPS that we are collecting the GPS data.
Yes. So that's a separate process altogether. We don't have anything to do with that when we are looking at the RAO.
Yes, sir.
Yeah. So after collecting different data, we get the wave time history and the pitch time history. So the wave time history we get it from the wave probe, and the pitch time history we get it from the IMU data from both phone and the XSense IMU sensor. So there is a very simple formula to calculate the RAO. So you just calculate the average pitch amplitude and divide it by the average wave amplitude. That will give you the RAO that for that particular wave frequency. So using the wave generator, a wave will be created for a particular frequency. For that frequency, what will be your response? That can be characterized using this RAO. So you can see on the right side, this is a general pitch RAO. We just found it on the internet just for a sample. It is just a sample image. So you can see for different frequencies, you are plotting the RAO, and at frequency somewhere around 0.4 or 0.5, you can see the peak. So that peak corresponds to the pitch natural frequency, where at that particular input frequency, the response will be higher. This is what this peak implies. So yes, now we'll see different graphs in coming slides. Yeah. So this is one of the data that was collected from the wave probe and the sensor, the XSense sensor. So this is the title of this image. You can see it is 180 HSZ13. So 180 corresponds to the 180, the experiment number. So it was the 180th experiment. HS corresponds to the head C condition. Z corresponds to a particular wave height, and 13. Sorry.
Stiffness.
Huh?
That
Yeah.
particular wave value from the wave stiffness.
For a particular wave stiffness, yes. So you can see there are two subplots here. So the first one corresponds to the wave time history, and second one is the pitch time history.
1 second. So Z corresponds to a wave slope, right?
Wave stiffness, yeah.
And the number corresponds to the wave period in some sense.
Yeah, that 13.
Correct. So that corresponds to 1.5 seconds.
1.5, yeah.
Okay, all right.
So yeah, the first subplot is the wave time history, second one is the pitch time history. So initially there will be no disturbance, and after the wave generator starts generating waves, slowly the amplitude, the wave elevation start increasing. That is the transient period, and after the transient period is passed, you will see more or less a steady value of wave elevation. So here we will get steady constant waves, and after the wave generator stops making waves, you can see the decay of waves here. So correspondingly, at the same time, you will collect the data from your sensors. So the pitch data is we can see in the below image. So at the same time, it is collected, and it has more or less similar characteristics. Yes, go to the next. Yeah, this is another one data which was found in that experiment. This is for 164th run. So there are certain differences in this data. So here the wave generation was started around 20 seconds after the wave probe started recording the data. After that, it was generated for more 30 more seconds, and then it was stopped. So you can see that there is a transient period, and then the wave goes, the wave elevation goes to a steady value, and then goes to zero. At the same time, you can see the pitch data. So the pitch data has a certain characteristics. You can see the linear upward trend in this data. So the reason for this can be like it might be due to the sensor, the noise in the sensor and all. That might be that might be the one which is causing this linear upward trend. So yeah,
Yeah, this
next.
is a drift which is very common in IMUs.
Yes.
Okay, you will see if you look at the yaw, you will see much more. An effect of that is kind of getting seen in the pitch a little bit.
Yeah, the solid line shows this trend, the upward trend. Yeah. Next. This is another one data which we found out. This is the 192nd experiment, and here there are certain different things happening. So you can see towards the right side of this top image, it is not a single frequency, it seems. So there are multiple frequencies in this signal. So why this might have happened? So the signal that was the wave that was generated for this particular experiment was having a time period corresponding to 4.01 seconds. So the wavelength for that particular time period was around 19.1 meters, 18 meters. Now our wave basin, the dimensions of our wave basin are around 30 by 30. So you can see that the wavelength of the wave generated is around 2/3 of the length of the wave basin. So you can clearly visualize that if we the wave that is generated, it will reflect back and it will interfere with the incident wave. So both waves will interfere, and they will cause the response that you can see in the top figure.
Why is
So
it
the
that
pitch.
your L0 that you computed 1.56 t square and the one from the wave table, why don't they match?
So this L naught is the deep water wavelength. So 1.56 into t square, that will be the wavelength in the deep water for this particular time period. And then we know the depth of our wave basin. So that is around 3 meters. So for that 3 meters, we will find the d by L naught. So that will be some value. For the corresponding d by L naught, we will find d by L from the wave table. And then we can find L. And that comes to be around 19.18 meters.
So this is including the so-called intermediate water or shallow water approximation, right? So that's the idea is that now the wave depth, or not the wave, water depth is starting to affect the wavelength.
Yeah,
So
yeah. So here we are not considering, here we are not considering that we are in deep waters.
correct. It is not actually in deep waters. You can see a considerable difference. It's almost off by 1/4, right? 6
Yeah.
meters over 25 meters is about 1/4. So it's a significant change.
Yes.
So only goes to show that doing tests at 4 seconds in our wave basin and assuming they'll represent deep water is not a good strategy.
Yeah.
Okay. So it only goes to show that there is some limitation to the wave basin in terms of what are the frequencies we can test, beyond which we are going to see a shallow water effect come into the picture.
Yes. So the wave that will be generated, it will reflect on one particular end of the basin, and it will interfere with the incident wave. So that is not the ideal way to test to get the data. So that's the problem in this particular experiment. Yeah. So next, yeah, now Vallabh will explain from here about the analysis of the data.
Am I audible?
Yes, I
Yes.
can see it.
So
So as we saw in the previous slide, like the data is having a linear trend. So so we need to remove that trend from the entire data. So it is necessary to get the proper analysis of the uh, wave amplitudes, and so we do that by linear regression, and we get that straight line, that this straight line as we are seeing here, and subtract all the data points, subtract the values of all the data points from this straight line value, and then we get the uh, as this is the original data, and you can see in the orange the trend lines, and then after removing that trend line we are seeing the difference. So for the pitch you can notice clearly it is trending upwards here, and now it is meaned out. The next step, this was the first step that we did with the data. Now the second step that we are going to do is we are going to filter out the unnecessary parts from the data. So uh, we are seeing that we can't use the entire data here. So as you can see in the this particular data was 164th data. So here the wave that we are providing is somewhere in the range 20 to 50 seconds. So corresponding to this region, the IMU data is coming from around some 80 plus value to before 120. So we need the response corresponding to this wave from this data. So we don't need the rest of all the data. So we have to filter that out. So the steps that we are going to follow are, like, first we will convert the entire signal from time domain to frequency domain. Then from this frequency domain, we pick out like as we will see in the plots ahead, we will pick out the frequency or the incident wave frequency and check a small region around that frequency, and we will use only that the, the data corresponding to only those frequencies we will use for our calculations later on. So we will filter out all the other frequencies. The magnitude of all the other frequencies we put as 0, and then we take the inverse Fourier transform of this region that we chose from the frequency domain, and we get the sinusoidal response in time domain. Now we identify the peaks in the data corresponding to this region, and we carry out the filtering process on this selected one data, which is the region where the response is actually happening, and we take the mean of that data and we get the mean amplitude. Now we will see the plots and discussion about how these steps are carried out. Manoranjan will discuss those.
Yeah, so this plot shows you the filtering process. So these three plots actually shows the FFT of the corresponding time signal that you saw for that 164th test case. So if you see the first plot in the top is for the wave. So you see a single high peak which corresponds to the wave frequency. And then when we are filtering, so what we are doing here is we have this mean frequency which is at the peak, and we choose a threshold beyond which we filter out the rest of the frequencies. So in the wave elevation FFT, this might not be very apparent, but if you look at the pitch for the pitch motions, this will be easily noticeable. So the blue line that you see in the plot is the FFT of the time history of the non-filtered wave, and the red line that you see in the plot is the filtered FFT. So if you see, we are taking a region beyond which the frequencies are not considered, and we are choosing this mean. I mean, we are choosing this particular. So in this particular case, if you see, there are very small frequencies with very great amplitudes. So we need not include those in our calculation, and that is those frequency values are the ones that tend to create the problems when we are taking the means. So we are filtering those values, and we are taking the the frequency which we require. So similarly, these two plots that you see in the bottom are from the XN's IMU and the IMU that is from the phones. So in this way, we will tend to filter out the data, filter out the irrelevant frequencies, and we reconstruct the time history from this frequencies that we have filtered out. And if before before this part, so after reconstructing from the after reconstructing from the filtered frequencies, we tend to calculate the region where we want to extract the relevant amplitude of the waves. So if you see this red region, that's where we would like to extract the amplitude of the wave or the pitch from pitch average pitch. We need to average the amplitudes from these regions. So to calculate this region, we are taking out like again we are trying to set a threshold manually. So using that threshold, we calculate the region in which this change takes place. And once we extract this time range, for this corresponding time range, we again we use FFT to similar to what I've told before, we use the FFT in this corresponding region and filter out the irrelevant frequencies and reconstruct the wave back, and from there we take out the average amplitude. So yeah, so that's corresponding to that part. So now this is the plots corresponding to the to test case 188. So here, as Aditya earlier mentioned, we talked about some issues with larger wavelengths, and smaller frequencies and large wavelengths. So in this plot, you can see that the topmost plot here corresponds to the raw wave relation. So the region between 10 to 20, you can see that they oscillate in a sinusoidal way, and it kind of the wave height slowly increases. So this corresponds to what Aditya has mentioned before as well. And if you see, and if you extract the region for which using the method that I have mentioned before, then this red line is the one which we get it. But we actually don't need this region between 25 seconds or 30 to those particular regions. After 25 or 30, we don't need, since those are the regions that are kind of being interacted from. Those are the region in which the interaction happens. So these things kind of make our automation process difficult, and even this FFT plot that you see here. So that thing, you can actually see a single frequency of the wave, but we in the FFT plot too, we are not able to capture that interference from the reflected wave. So all these kind of makes this process a bit difficult, in which involves larger wavelengths. So can you go to the next slide? So this plot corresponds to, the previous plot was for wave motion, and this plot is this plots correspond to the pitch from the XN's IMU. So here too, as you can see, after the transient state, you kind of see a steady state response. But again, after some time, like 30 seconds or something, you see a weird response in pitch. So we are not able to filter out this corresponding part, and this, as I mentioned, this tends to hinder the process for RAO computation at larger wavelengths. Yeah. So similarly, for the next slide, will show you the plots corresponding to the phone IMU. So here too we are observing the same thing. So yeah, next slide. So after we have computed the wave RAO using for the phone and the IMU, so this plot here, so the black line is actually the plot from Hydra, and this blue line corresponds to the phone IMU data, and the red line corresponds to the XSense IMU data. As you can see, for lower frequencies, the wavelength doesn't, the RAO doesn't seem to match well with what we compute using Hydra. So this, as we mentioned before, might be probably due to the interference from in the wave basin. So yeah, so what we think is that we probably have to manually select the range for these cases in a looking at manually, we may have to select the time region. And so what are the works remaining? So as I mentioned, so we have to determine the pitch RAO for the data corresponding to the improper cases that we are observing. We are still working on that. And once the pitch RAO is done, we will be moving on to the calculation of the Heave RAO, which is more challenging. And the next aspect is to calculate the full scale RAO for the pitch and heave motion, and in Hydra simulation, and comparing with whatever we have obtained experimentally. And yeah, that's it. So thank you. We're good to take questions.
Can you go back to the slides where you are doing the frequency domain calculation? Yeah, here. So can you, I didn't understand what the blue line is and what the red line is.
The blue line corresponds to the FFT of the actual time history.
Okay.
The red line corresponds to the plot after filtering the lower frequencies. Filtering the frequencies that we don't want. So if you see in this plot, one second. So we are actually we are determining a threshold. Okay. So if you see the actual frequency that we want corresponds to the frequency around 9. Okay. So
yeah,
we are filtering out the frequencies which are, say, less than 7 and more than 11.
Okay.
So as you can see, like the red line will flatten out from frequency 7 and from frequency 9. And you only have a single peak, which corresponds to the pitch response.
Yeah. What is this light blue line?
Light blue line corresponds, it's just like for reference, so it corresponds to frequency 2 pi by 3. Am I right, Vallam?
Okay.
It's just a reference.
That line actually does have a meaning. I wanted to kind of see, that is where the roll natural frequency is. So if at all, when we were doing the RAO tests, whether by any chance, if we were exciting roll into the case, where we were not purely measuring linear motions, but some funny behavior was coming in or not, I wanted to check that at that frequency. That's why that line is there. So that corresponds to the roll natural frequency.
Okay, sir.
Yeah. So have you thought of any ways to remove that interference?
Yeah, that one we are so it's quite difficult. So if you see in the frequency domain plot of that, yeah, so it seems to be a clean one. Clean in the sense like as far as we could observe, that interference is not being captured by the frequencies, I suppose. So yeah, so we are trying to resolve this issue, but I think automating this for unlike the previous case might be difficult, and we should probably do this on a case by case basis. If you can think of any suggestions, that will be helpful as well.
I was thinking of one thing, but I'm not sure if we'll be able to implement. So if we know the distance between the wave probe and the wall, and we'll know the wave velocity, so we can calculate the approximate time it would take for the wave to reflect back. We can cut the time series at that point.
Yes, so
Indeed, go ahead.
That is what we were thinking from parametric rule group.
That would be a perfect way to do it. Since you precisely know what is the wavelength of the wave, and you know that it will come, the reflection will come back in so and so time, based on the fact that you have 30 meters of wave basin length. It's a little more than 30 meters because we may be 10 meters away from the wave basin, from the wave maker. So we have 20 meters for it to go to the beach and another 20 meters to come back.
Correct. So we just calculate that time and
right. So for a conservative estimate, you may even choose it as 30 meters rather than 40 meters as the distance which it needs to cover. So from the moment you pick the peak, where you start that red dotted line, wherever you are starting that, right? You say that I'm only going to look at so many wavelengths depending on how much is the wavelength versus the wave basin length. Based on that, you say I'm going to look at only 4 waves. I'm going to only look at 3 waves. I'm going to only look at 2 waves. I'm only going to look at 1 wave. The method fails once you come back to 1 wave because you really can't pick 1 wave out of it or half a wave out of it, right? But at least you can pick up to 2 waves or so. If you can get, you can map the left hand portion of your RAO much better. So rather than figuring out the reflection from your FFT, Nimesh has a very good point that once you know the wavelength, you can say that so many wavelengths, I'll cut it off.
Yeah, so in that FFT, since they are in the same frequency, we are not able to.
Precisely, the reflection will also be at the same frequency. The wave frequency will not change. So you will see a beating kind of a phenomenon, which is hard to isolate out when you look at the signal, right? And some of it is actually a standing wave component too.
Yes.
Put on top of a, what you call a progressive wave component. The standing wave part might be smaller, so it's very hard to distinguish it and pull it out. So it is better to use that approach which Nimesh is telling you and try that out. And actually, it does seem to yield better result from what I have been trying out. Yeah, please do try that out. I'm also trying it out to see. That seems to give much better result. But somehow, funnily, I've observed, if you look at the IXNs versus the phone and the low frequency regime, you'll find that there is a difference in amplitude between IMU1 and IMU2's predictions.
Yeah.
See, for example, here it is 1 degree is the amplitude. Go back. It's almost more than 1.5 degrees on the XNs.
Yeah.
I do not know why this error has crept in.
And that's why there was a larger difference in that plot.
Correct. Between the phone and this one, there is a larger difference, which I am observing there. And I'm not quite sure I understand exactly why that is coming. My first suspicion is that the phone may not have been flat. It may have been at a little bit of a pitch angle itself, or it may have been a little cross. So it may have been a little cross because of which there may have been a difference, right? So I do not know whether that is what is the cause of the problem. But nevertheless, I am seeing that the pitch degrees or the pitch time history is under predicted from your phone. Okay, so typically it is falling below the curve, but from the xsense we are getting pretty good result, I think. The other thing is, what do you do about Heave? Any thoughts on the Heave?
Probably, like as we discussed, we should, yeah, last time we discussed like we should double integrate. We have this acceleration, Heave acceleration. We may probably have to integrate it, but that will surely lead to accumulation of errors.
So what approach can we think of? Any other thought processes?
What is happening with Heave?
We don't measure Heave directly, no. We only measure the Heave acceleration in an IMU. We don't get actual Heave velocity or Heave displacement out. The question is how to get it. My thought process would be something like this. Take the total acceleration vector which you get from your IMU and form a rotation matrix from the orientation. So transform that acceleration vector into the so-called inertial space. Right now it's in a body fixed space, right? The frame is actually moving with the body. So if I move that into an inertial frame, then I can take the FFT of the signal, do the similar process of cutting off the frequencies away from the area of interest. Whatever amplitude I get, I divide it by omega square because I precisely know the omega that I wanted to simulate it for. Since its acceleration, it should be minus omega square times the amplitude. So if I divide by the omega square, I should technically get the amplitude for the Heave. Technically. Right? That might be the best approach, I would think, rather than attempting to integrate it.
Yeah, that will separately lead to accumulation.
The moment you start integrating, what will happen is you will create a drift and a linear variation as well, so which you will have to account for again. But this way, you can directly compute it from the acceleration, and you know that it should be minus omega square times the amplitude and the acceleration. So it might be a better way to do it. Okay, so basically what we do the same filtering process, but we also divide by omega square before reconstructing the time series. And then once you reconstruct that new time series, that should be looking more or less regular and find its amplitude should give you more or less a Heave value.
Yes.
Okay, this is a process which I'm yet to try out on the data myself, but I'm hoping that let's see how good or how bad it goes. Since the angles are small, it should not make much difference even if you did not do the transformation, but the right approach would be to do the transformation into the inertial frame first and then do this process. I think that would be the right approach to do.
Okay.
Okay, all right. So sounds like some progress is being made, but some more needs to be done.
Yeah.
Okay. All right. Okay. Well, can we try to see if we can come up with the RAOs by next week?
Yes, sir, sure. Yeah.
So that we can kind of try to. The experiment has been done quite a while ago. I don't want to hold on to the data for too long before we start forgetting what was happening with it. So let's try to meet next week, and next week let's try to see the active comparison between the corrected pitch and the corrected Heave, and let's see whether we are able to match. I also want to see if we can do this for the oblique waves, because we also have data for 30 degrees oblique waves, or technically for 210 degrees orientation. So it might be worthwhile to investigate that as well if we are getting a good success with the head C condition. Okay. So let's try to do that and see if we can get that out, because the match seems pretty good. And we are actually right now comparing Hydra with Vamit.
Oh,
So we are seeing that it matches pretty well, but there are some small issues, especially with pitch and some coupled modes, where we are seeing small differences. I'm kind of curious to find out whose RAO matches best, ours or Vamet's matches best. It may actually not be much showing up in the RAO, possibly. It may be something which shows up only in the forcing as well as in the added masses, but may not have significant effect on the RAO, but nevertheless we want to kind of see that. And the group which has been working on the Hydra, they are preparing to write down a paper on this. So it will be useful to have a experimental comparison as well in order to get that going. Okay, all right, sounds good. Any other questions, queries, or thoughts or comments on the topic? No other thoughts? In that case, we can stop recording, I guess. And no, before I stop recording, there is one other thing. One other aspect which I want to kind of see is that gazebo modeling for the KCS which we have. Let's try to put the, I want to kind of see that reflect the correct dynamics of our craft in some sense. Right? There is multiple cascading steps which we have to figure out. Yeah, we'll need Ashwin's stuff for predicting the coefficients, and we'll need an indoor positioning system. Yes, this is something which I probably did want to share with you. I was having an interesting discussion with a colleague here, and someone pointed out that there is a cheap positioning system, indoor positioning system, which is available. It's called POSIX. So let me kind of share my screen maybe. See if that is. Okay, so it's an ultra accurate indoor positioning system. And what it basically does is that they have a software integrated together with it, and it's a hardware is a set of it works off of what we call as this thing, ultra wide band. So it's working off of an electromagnetic wave spectrum, but ultra wide band is the new technology which is coming in for positioning. So it's using the same concept as a GPS. You have receivers, 4 receivers, which are 4 transmitters and 1 receiver on the board. I don't know which one it is. Is this the other way around, I'm saying? Okay, let me see. Products. So I was looking more for this, what you call developer kit, creator kit Lite. Maybe we can go for the creator kit. Info. This is Asia Type C. Okay, what does it come with? It comes with 3 power banks, 5 power adapters, 5 Velcro, 1 micro USB, multiple tags. Okay, so I think these are the tags. These ones which you see here, they are the tags, and this is the board. Okay, accurate musing using 9-axis sensor fusion, compatible with Arduino and Raspberry Pi, and accurate ranging between devices.
Sir, are they usually used in like warehouses or something?
Yes, that's right. It is actually used for different warehouses like Amazon and things like that are using their enterprise version. Okay, and it's 10 centimeter accurate. So this got me thinking that it's not quite expensive. Seems like reasonable amount which we can spend to get it. If we can put it in the wave basin, we can know our precise position of the boat, and that will help us. One of the problems which we are facing right now is speed calibration. We don't know at what speed to run the RPM in order to get a certain speed of the vehicle, right? If we have such a positioning system where we precisely know what is the speed of the vehicle from this positioning, we can precisely run it at different RPMs and see what is the speed we are getting.
Yeah.
So it will help us figure out a open loop control signal mapping to what is the speed of the vessel in the straight line case. We can also look at putting it in the wave basin and turning it around at different speeds and see what is the speed loss when we are executing a turn. It won't be the same speed as what we observe in a straight line case. There will be a speed loss when it's trying to turn because it has a drift angle, right? So it will not be as effective. So there will be an additional resistance which will cause it to slow down. So those aspects can be precisely measured. Right now, we are not able to measure them. I originally thought the GPS may be enough to figure it out, but looks like it may not be. So therefore, we might want to go for something like this and get a precise positioning is what I'm thinking. Can one of you get in touch with them or a demo? I know that they are offering some demo services. Can you talk to them and organize a demo? Most likely it will be a virtual demo, but I think it will be worthwhile to see and investigate whether it will suit our application or not. We can have a discussion with them. Can someone volunteer for me?
Yeah, maybe I can try.
Manoranjan, you'll take care of it?
Yeah.
Okay, all right, fantastic. So let's try to see what's going on with it. Okay. All right, anything else? Nothing else? In that case, we will stop recording here.